Oh, just had to press it again. Worked for that time. Well, it's official. We are now into week 4. Congratulations, folks. At the end of this week, we're 25% done with the entire semester, so it's going quick depending on how your point of view on it. We have a lot of announcements just kind of scattered around here, but any questions that folks have to start us out? Okay, well, running through the announcements, let me temporarily hide them. We have quiz number 2 up here, which is going to be due on Thursday. I'll be posting a new one down below right here as well as we get closer to the end of the week for our course. Other things to mention about the announcements are these sections here that we're doing this week on 2.5, 3.1, these sections are going to end up on the second exam. So that way, only these sections right here being on exam 1, those would be the sections that you've had ample time to work in on WebAssign, do the associated quizzes with, and get feedback on these kinds of things. So usually the week right before the exam, it's going to contain sections that are on the very next exam. That'll be the pattern that we do as we go from week to week, exam to exam. As far as the exam itself, it's going to be a 75-minute timed exam, whether you're in the Pocatello Testing Center or taking it here in the classroom. And for folks do taking the exam in the Pocatello Testing Center, sorry for the 2 emails I sent out. Our exam is on Tuesday, not Monday. Have to get the Monday thing out of my head. So what'll happen on Tuesday is people in the in-person section will just be taking the exam physically in the classroom here. And people who are taking their exam at the Pocatello Testing Center, you'll make arrangements with them. It's in their new location, Albion Hall. But that means there'll be no actual official class on Tuesday of this week right here. So even if you're in the fully online section, the Zoom will be empty since we'll just be doing an exam that day, which is good. There's a little pause in the course on this week right here because of that. Other things about the exam is it's closed book and closed notes. However, this document right here is the exact verbatim last page that you'll see on the real exam. And you will definitely need a scientific calculator. Maybe not as much on exam 1, but for other exams, you'll definitely need it. We'll see occasions where I'm pulling up a calculator, putting in approximations. So it's just good to have it with you on exam 1 even, just as a habit. Be sure it's just an ordinary scientific calculator since the graphing calculators aren't allowed for the exam on this course. Well, any questions about the exam so far? Okay, more things going on the Moodle website down here on the exam week are that we've got a lot of documents down here, so we should discuss them. Again, this is a document that you want to have pulled up on a browser window, maybe printed out even, but you don't have to bring it to you on the real exam. It is the literal last page on real exam 1. So the reason this is so important to have pulled up is when you're studying for your first exam, you want to know what's on the table as a formula sheet, pretty much just the limit laws. And that informs you on the things that you will have to have memorized for the purposes of the exam. So keep this at the ready as you study. Then you can use either of these documents here to start studying things. If you notice that, hey, there's a formula or there's an idea or something that wasn't on this formula sheet, make a second formula sheet of just things you have to practice and be ready for on the upcoming exam 1. And that'd be a great way to organize this information. So that's the formula sheet. And then for all the exams, exam 2, 3, final exam, we're pretty much going to have documents just like this. Sample exam 1 exercise version 1 is problems from the online textbook. So it's these problems specifically. They're primarily odd problems. You can go to the online textbook, the relevant sections, go to the back to see the exercises. For each one of these, I felt like these are great problems that could make decent exam questions. Because they're odd problems, you can click on show answer to see how you're doing as you study these. So that's one avenue. There are fresh problems right there. Another way to study is you could go to this version 2. This is lecture notes converted into worksheets. That doesn't sound exciting, but the idea here is If you're studying for exam one, you really don't want to go here and just eyeball it and read it, because that's not what you're doing at all in the exam. What you're doing on the exam is filling in this information. So these notes, well, they're good to come back to, but only when you're over here. If you decide to use this document, this is more valuable because this is the same sections, but I took out all the noise. There's no formulas in here. There's no limit laws, nothing about remarks. This is what an exam question could really look like. So if you fill this out, you'll have a check on your work just by going back to the relevant section 2.2. So it's a really long set of notes. This thing says it's 10 pages. But again, this gives you a good idea of what are the fair questions that could turn into exam one questions. So scrolling through here, same problems that we've been doing all along. But honestly, no one memorizes these problems verbatim. They're still equally helpful in preparing for the exam. Any questions about these documents so far? Okay, so a very common question about the upcoming exam is how many questions are there going to be on it? Is it similar to any of these documents? And my exams are honestly kind of short on this class. I'm not trying to write an exam where your hand has to be moving the entire 75 minutes you're there. I'm more trying to write about a 50-minute exam with the extra 25 minutes built in. That's just trying to check your work, that kind of stuff. So I would say the most similar questions to the first exam would probably be a tie between these two documents. But there's a third document. If you want even more fresh problems, more challenging, some of them are very challenging, this would be a great document to take a look into. I would say for most people in this class, when you're studying for an exam, usually you want to go to here probably last. It's just another set of more questions with answers at the very, very end. But again, keep in mind, some of these are a little bit more challenging than before. Not all of them can make actual real exam questions, but they're still valuable along the lines of if you're studying for an exam, you don't want to do all the easy questions. Sometimes you want to do hard questions, so you're prepared for the middle of the road questions on a real exam setting. And that's that purpose of that document. Well, any questions at all, folks, about any one of those materials? Or anything in general related to the exam or otherwise? Gotcha. So the question was, do we have to memorize these? And no, these ones will be the literal last page of the exam. So these ones here are the ones you don't have to memorize, is what's being said here. But also means if you go from section to section as you're studying, there'll be a couple things that you really do have to memorize. For example, let me see here, would be a good one. We have some pretty good information on all of these right here. But if we go to section 2.2, let's see if we can find something that we would have to memorize. Let's see here. There's a lot of stuff. You need to memorize, say, the concept of how a horizontal asymptote corresponds to the value of a limit, if and only if we're going to infinity or a negative infinity. So it's going to be those little concepts that you would be expected to have memorized. But these ones here, these will be provided. Other questions so far? Okay, so let's imagine it's like Friday of this week. You're about to start studying for this course. I would say a really good, say, order of operations for studying would be the following. Make sure you've got all of your quizzes in. I'm going to post a third quiz. It's going to be due on Thursday, which is awkward. The exam one is on Tuesday. But if you do solve quiz 3 early, I'm going to make every effort over the weekend before Tuesday to get it graded, sent back to you, so you have an additional feedback on what could be a potential real exam question on exam one. So I'd start by 1, make sure you're caught up on all those quizzes, that you understand the feedback I provide on it, or maybe you just got 10 points. That means your work on there was perfect. After you're caught up on quizzes, there's only going to be 3 to get through. Next, you'd want to go into the Web of Science system and just get caught up on any section that you might be a little bit behind on. And let's actually go back right in there today, just to emphasize one thing we haven't shown yet, how to request an extension on there. So let's imagine, for example, a due date passed maybe on section 2.2, but you do want to go back to work on that for the purpose of studying on the exam. This is what you would do next. First, let me log in real quick here. It's about a 15-second mental break. Need to change that password one day. Okay, so in this WebAssign, I have done 0 homework. So I've been really behind, but the due dates are arranged so that it's always a 1-week turnaround after we finish a section. So really there's only one past due assignment. They'll always say which ones they are by this tab right here. As far as due dates go in this class, if you really scour through a syllabus, you'd notice there is no late policy whatsoever. So even if you didn't get quiz 1 in time, I will still accept it for full credit if you get it in before the end of the class. And same thing goes for these assignments here. Think of the due dates as really it's just a benchmark that you have to hit to be considered fully caught up for the course. If one passes, I'm not going to penalize you if you decide to go back in there and study that content. I think that's terrific. And I expect everybody's week is chaotic sometimes. There'll always be some weeks where it's just hard to get into the system. And so you have to do some catch up. So click on the past assignments link right here. Then what you want to click on next is request an extension. Here, you have to say the new date you would like. I'm not too picky here. So if you decide to make it, say, 1 week out, say the 11th, that'd be totally fine as well. Again, there's no late policy, due date policy, that kind of stuff. So use your best judgment. And even if you're requested an extension and your extension date passes, you can request another extension. So it's not going to harm you in that kind of way. For what you would put down here, you can say anything helpful, but I just want to emphasize you do not need to say anything whatsoever. Since it might be a personal reason why you need an extension, and you don't need to share personal information that you're not comfortable with. If it relates to something about what's going on around the ISU campus, your other classes, that might be a little bit more pertinent. But again, you don't have to tell me that information. So if you leave this totally blank, that's okay. No judgment whatsoever. I would probably worry about this right here. Try to get a normal time, like say 11:59 p.m. That might make more sense. But click on submit. And it says, well, you have something that was requested. Takes a minute for the action to occur on my end. After you click on requesting an extension, then back over here. Sorry, let me move my windows around. Oh no, I left the whole thing. I didn't mean to do that. Let me get back in there. You got a question here first?
Yeah, just to make sure these assignments, they kind of just turn themselves in when you do them, right?
Correct. Every time you put in an answer, your grade on the assignment pretty much auto updates. Oh, this is where I want to be. So after an extension was requested, this is what I see on my end. I also get an email through my ISU email account to notify that extension's been put in. I go in here. No, I don't do that. I go over here. I forgot how we do this. Go over to communications. I go to the requested extension. That one was from Michael Jacobson. I click on this and I just go grant extension. If you gave me any information, I'll read that to make sure that I'm aware of what pertinent information might be there. And if I decide that maybe you need another day, maybe you requested an extension that is only active for 6 hours, I might push it out a little bit further just out of convenience and click on there, sending it out. So there's a little bit of time delay between requesting an extension and getting the extension put in. So that means it's okay to do a little bit of planning there. Make sure you're requesting an extension, say, not right before working on that section. Try to get it in early so I have time to put in that extension, and you'll be all set for actually working it when you intend to. So just to reiterate, you can request as many extensions as you would like. There's no harm, there's no penalty in coming back and working on these problems. You still get full credit. And it also can sometimes reorganize where this is going to fall whenever you do that. Let me see here. This should have updated. Looks like it takes a moment for this to update. It says it's extended until, oh, I extended it to January 31st. That wasn't helpful. We're in February. So if I extended it correctly, it would have shown in the right list over here. it might be reorganized because it's now has a new due date. So you might have to hunt for it potentially. But any questions at all, folks, about requesting an extension or any of those matters? Okay, so back over here to this really long statement I was trying to make. If I was studying for exam one in my own class, I would first make sure all the quizzes are caught up, turned in. Second, go back into WebAssign and work on any problems I didn't get to. I mean, that's doing two things. Homework is worth a lot in this course, and so you're getting the homework credit and studying for the exam at the same exact time. And I would focus specifically on these sections. Because we're getting towards an exam week, it's not a bad idea to focus in and narrow down our working on just those. After I'm fully caught up on those, then I would start looking into these additional documents. You'd probably have a good idea of which section is bothering you the most, the more tricky one. Maybe it's 2.2, maybe it's 2.4. And from any one of these, you could just target that section. Do the problems in section 2.4 over here or in any of the documents down below. So that would be a great way to study for this course. And well, as we go from exam to exam, we'll see how any updates we need to make to that kind of studying as well. If you feel like you want to ever change your study habits, this optional reading down here is a great one. Okay, that's a lot of announcements for us today, about 7 minutes worth. But any last questions at all, folks, before we go back to section 2.5?
So for the practice exams, are the solutions in the textbook somewhere or a sheet for that on Moodle?
They would be in the textbook for this one. For this one, these are up on the Moodle website. So if you're working through this document and say you're in section 2.3, working example 2, you would just go to Moodle, section 2.3, pull up the example 2 there, and that would be the solution for that document. It's a little bit tricky. It sounds like it's different from every single file. I'm really glad you asked about that. So this one, you can find the solutions in text. This one, you find the solutions in the Moodle documents. This one has solutions at the very, very end of the document. So this one is the pretty big document right here. But does that help out with that question there?
Yeah, thank you.
Yeah, absolutely. And thanks for asking that one. I feel like sometimes the version 1 is the least popular of all the sample exams because really to work this file, you have to go and do the following. Go all the way back up here, log into WebAssign once again. Then let's say right at this point, you've logged into WebAssign. Then you've got to click on My eBooks. We're getting there. And then you have to go, don't know what that is. Let's say again, we're looking into section 2.2, those problems there. Go back to this, go to the chapter 2. It's kind of tedious to be honest, but it's nice to have the textbook just always available. Click on the menu bar here to target section 2.2, exercises. Now, finally, we made it, folks. In the section 2.2 exercises, through this document, I said, these are very well represented problems for what could be on the real exam. Let's look into problem 25. Not that 25 is super special or anything, but it would say try out this limit. And the answer is also displayed right down below. This one's going to infinity. And because we have 1 over t squared, this is becoming e to the power of 0. That's why it's becoming a 1 on this one. So that's how to get to the solutions on the version 1, the sample exercises. Honestly, a little bit annoying because of all that clicking around, getting into the textbook. But once you're there, these are excellent exercises to take another look at. Other questions at the moment? Okay, maybe one more thing to mention. If you also took a look at the day-by-day syllabus for the course, it's a lot of tabs, geez, which has, I'm reminding myself we meet on Tuesday and Thursday. That's been really hard to remember for some reason. You notice we don't have a review date built into our syllabus. It's a pretty full day-by-day schedule. But even though there's no review day built in, every class meeting, we always start with calling for questions. So that means when we come back on Thursday of this week and we call for questions, if you happen to have lots of questions relative to exam review content, I'd be happy to work with everyone on those kinds of questions. So even though there's no full review day built in, we can always start with a review right before an exam day. It's up to the students. It's a student direct review. So again, on Thursday when we come back, if you have questions relative to exam one, don't hesitate to ask. But I'm also available through office hours. I'm available in the tutoring room, and I'm available very extensively through email, even over the weekend. So any questions come up as you're studying, don't hesitate to reach out one way or another. But I think those are the major comments I want to mention about getting going with exam one. I've probably said this a few times, but one more time. Any last questions at all about exam one? Okay, well, even though section 2.5 isn't on exam one, we still have to move forward through the schedule. This one will be on exam two. But you know, it's some pretty related stuff. That's a rough page to start out on. It's some pretty similar stuff because we're still looking into limits. But now we're looking at them through the lens of continuity. We looked into this document last Thursday, which is rough because this is pretty technical and a weekend is a long time. So just as a refresher, continuity just means you have direct substitution working in the problem. That you could literally take this A right here, plug it inside for F, and get F of A. Whenever this equality works, where the value of A becomes F of A in the limit, we say we have continuity. But visually, continuity means we can sketch a curve without ever having this kind of problem. There's no holes. This is a discontinuity. There's no breaks like these. We call these jump discontinuities. And these are more jump discontinuities like we saw. And here we saw all sorts of discontinuities. We call this one a hole, or excuse me, a removable due to the hole in the graph. At x equals 2, there's another hole in the graph, so it's a removable discontinuity, whether or not a function value is defined. But x equals 4 was special. On this one, the curve was at a certain height, height 2, but then when the x value moved past 4, it jumps. It would jump down to a height of 1. So we call that a jump discontinuity. And one thing that's special about a jump discontinuity is this limit would never exist. It's undefined. However, the right side limit, well, that's at 5. The left side limit does come out as a 2. The right side limit does come out as a 1. And finally, up here was the infinite discontinuity. Anytime a vertical asymptote occurs on your graph, we've lost continuity in a major way as well. It's not like these. You can't fix them by redefining a point. So we just called it infinite discontinuity. So those are all the types we're going to see in our class. There are other weird things that functions can do. But what we'll do next in part B is determine whether the function is continuous from the right or the left at these discontinuities. That's actually really, really tricky right here. So we'll refresh what we mean by continuity from the left and the right before we start this one. But any questions at all, folks, with a refresher on example 2? Okay, so let's give this a try. When it comes to continuity from the right or the left, it's technical, but sometimes you can read it off the graph. So here's the trick. The technical nature of it is continuity from the left means the function value has to match with the limit, and it has to be a left-handed limit that existed. Continuity from the right, on the other hand, means the function value has to match the limit only when you come in from the right-hand side, and we get the same outputs. If you're reading it on the graph, continuity from the left means as you go left from right, you landed on a solid dot. You're automatically continuous from the left. Not from the right on this one. We don't land on a solid dot. Here, as we come down, that's an open dot, so we don't have continuity from the left. However, if we come down this way, from the right moving into 3, we land on a solid dot. So that's why we said it was continuous from the right here. Honestly, it's a lot easier to read it off the graph, so that's why we have this here. And let's try it again on this problem down below. It says for each discontinuity, so we need to make a statement for all four of these numbers, starting with x equals 1. And this one is tricky right out of the gate. Would you say it's continuous from the left or the right, based off the idea of landing on a solid dot? Neither is what folks are saying in class, and I agree. If there's no solid dot here, there is no single-sided continuity whatsoever. So let's say at x equals 1. Let's see here. We could say it's not continuous from the right, it's not continuous from the left, but let's just say neither, so we don't have to write so much. So neither here means no single-sided continuity whatsoever. Same issue over here at x equals 2. When you come in from the left, you don't land on a solid dot. The solid dot is way down there. Same as you come in from the right. So x equals 2, we would say neither as well. Now let's go to x equals 4. X equals 4 is different though. This does have single-sided continuity. Would you all say it's continuous from the left, or is this continuous from the right? Absolutely. From the class, folks said from the left, and it's all because as you come in from the left, we land on the solid dot right here, so that means continuous from the left. Another way to think about this, to think about the actual equation for continuity is, we could say, thinking of this point right here, sorry, that red dot's not supposed to move, let me try again. F at 4 is equal to this height of 2. Now, relative to 4, there's two limits you can take. You can take the limit as x tends to 4 from the left-hand side. You can take the limit as x tends to 4 from the right-hand side of the functions f of x. Now, if we do the left-hand limit, from the left-hand limit, it's getting closer and closer to a height of 2. So we draw in a 2 there. The solid dots and the open dots are irrelevant to the limit. That's one thing that's really weird in section 2.2, 2.3. Now, as we do this one, coming in from the right, we're falling down this curve, getting lower and lower to a height of 1. If there is single-sided continuity, it would be where the function value matches a limit value. Then, if we said it's continuous from the left, it should be because where it matched on the limit was a left-handed limit. So it's good to see how it works in the graph, but it's also important to see how it works this way analytically, just through the definitions. But this is a little bit tougher to tie in. Well, aside from x equals 4, we go to 5. But x equals 5, this one is a neither as well. Whenever it comes to a vertical asymptote like this, we neither have left continuity nor right on this one. There's no solid dot we're landing on the left nor the right, in other words. So we'll say neither on this one. Well, I would say the most important part of this problem is part A, just classifying the different kinds of continuities. That could be a really potential exam 2 question. Part B is important, left side continuity, right side continuity, but this is absolutely the tougher question. Any comments on getting through this one at all, folks? Okay, well, this is all visualizing continuity just through the graph so far. What we want to get good at is using continuity in evaluating limits. To get there, we need some more related facts, relative theorems about continuity. That's theorem 4, 6, 7, and 8 right up here. But think of this huge wall of text, all these different things here, as being not too different from when you looked at the limit laws for the first time. That's 11 different laws. But when you did these in practice on real homework questions, real quiz questions, you might have noticed you didn't have to have all of these memorized verbatim. It's just a list of things that you're allowed to take for granted. And that's similarly what's going on right here with all these properties. But before we do that, we shouldn't skip around example 3. I forgot there was an example 3. This one I put in a warning. This is a question that can be asked on exams, possibly exam 2 or the final exam. Probably not double jeopardy, that seems kind of rude. But what makes this an important question is, it's easy to think about continuity as it relates to the graph, but the actual equation for continuity, this stuff, that's the hard thing. So let's write this out carefully just as a review of how this all goes. We'll say that the function f is continuous at the number 5. We need an equation, so we literally have to say something equals something to make a full expression on part or example 3. So for continuity at 5, this immediately implies there's a limit going on. We can say lim as x tends towards 5. So this part of the expression is informing us what the limit will be. Because it's relative to a function f, the function f goes into this input position to the limit. Let me just recenter my equalities. And now finally, to say something is continuous at 5 means it's essentially direct substitution. Whatever value this is, just drop it in right here. And that's the full equation for the continuity at 5. It didn't say continuous from the left or the right, so that's why we just put 5 itself, not a single side limit. This is easy to forget when it comes time to thinking about this once again. So this is a good one to come back to and think about as we go throughout the notes. But I guess that's example 3, kind of a short question here. Any questions at all while getting through that one? Okay, another takeaway with example 3 is basically all we did in example 3 was we went up here and we just said continuous at 5, plugging in 5 into those 2 spots. The reason that we're emphasizing that so much is there's a difference between determining continuity through graphs and actually using continuity on these problems down below here. When we go to use continuity, if we're always well ready to go with it's just direct substitution, then this is what this is trying to say to help out. Well, any questions at all, folks, with example 3 before we take a look at those theorems below? Okay, well, it turns out continuous functions are pretty much par for the course. It's not easy to always to write a discontinuous function. Maybe in algebra, you had a rational function with a vertical asymptote. That would have been discontinuous. But there is a huge class of functions that are continuous on their entire domains. That's what theorem 6 is trying to say. And then once you know you have 2 continuous functions, say f and g, you can recombine them in the ordinary ways to get still more continuous functions. So theorem 4 is saying if f and g are continuous, the sum of the functions is continuous, so is the difference. Any constant multiplying a continuous function is still continuous. You can even multiply continuous functions. You have a continuous result. And just be careful on division, same with the limit laws. Division of 2 functions is continuous, so long as we're not ever dividing by 0 at any point. We would lose continuity at a if g of a was 0. So this is essentially telling us we can recombine our functions in the ordinary way and still have a continuous function. Theorem 6 is more of a catalog now. It says all of these functions are continuous at every number in their domain. It's the polynomial functions that we've discussed before. Power and root functions. These would all look about like this. Say for a polynomial, it could be f of x equals x cubed minus 5x plus 7. Doesn't matter what polynomial we put down. This has domain all real numbers, and it's continuous on its entire domain. If we say a power function, we just mean maybe g of x equals x power 12. That's just a different way to say a polynomial. It's a polynomial with one term, x to a power. For root functions, this could be, say, h of x equals maybe a cube root, a 5th root, 12th root of a value, or maybe just say x to power 1/3. This would just be a different way to say a cube root. Not too different from the power functions. As long as you're in the domain of this one's all real numbers, you're fully continuous. Then there's a whole new class of functions, the exponential functions. Rational functions, trigonometric functions we're not discussing as much in this class. There's no prerequisite to it. So anytime reading comes up and you see sines, cosines, tangents come on, that's still good reading. But if you skipped it, no harm done. You'll never be penalized about trigonometric content. But just to fill this out, exponential functions could be things along the lines of y equals e to the x, or maybe f of x equals 7 power of x. I'm running out of colors, but for rational functions, this could be a function, say, f of x equals x squared minus 5x divided by x plus 7. That makes it rational. Let's skip over the trigonometric ones and the final ones. These ones turn out to cause the most trouble in this class. Logarithmic functions. Because of that, we're going to do some review on logarithms just to help us out when we get to that content in chapter 3. But keep in mind, this course does have a prerequisite for logarithms, making this last class of functions pretty challenging for us, but we'll get through it. Logarithmic functions are stuff like f of x equals the natural logarithm of x. It's the inverse function to this one, the exponential function, because the base of this logarithm is e, Euler's number again. Or it could be something more direct, generic, like say log base 8 of x would be just another logarithmic function. So all of these different classifications of functions are continuous on their domains. And finally, well, there's a couple other tricks here. Theorem 7 says if we have f is continuous at b, and that the limit of g of x equals b, the limit operator can commute inside the function f. Or said another way, if g and f are continuous functions, then the function composition is also continuous. And that's what's happening with this operator right here. So that's a lot of stuff to absorb. We'll think of this information again as we go fill out the example down below. But any questions at all, folks, with the discussion of all these classifications of continuous functions? Okay, well, in example 4, we're just back to taking limits. So let's give this a try next. We want to take the limit as x tends towards 0 of this big mess. And notice the kind of functions we have going on in there. The square root symbol here would be a rational function, or root function rather, not rational. Let me try again. The root symbol here means we're dealing with a root function. So not too different than, say, x power 1/3. The thing on the inside, well, that one is just a rational function, much like this f of x right here. So that means this whole thing is a function composition of continuous functions. Your mate is on the table and says it is continuous at a. But keep in mind, continuity on a means you get to do this. Let's put this here just as a quick motivation of what we're about to do. The value x equals 0 is going to go inside the function f right here. This is the continuous function. That does deserve an exclamation mark because it tells us you actually don't have to work too hard on this. The expression that we have above feels abstract because we filled in the actual function f of x. So the f of here would just be recopying the root. In place of x squared, I'm just going to put a placeholder, 2 parentheses, one open, one closed. And for the 5 that's highlighted in yellow, in our problem, we're just going to put in a 0. So 0 goes here and here. This works because 0 is in the domain. We didn't divide by 0. In section 2.4, we showed what the tricks are whenever the function actually was not continuous. It's either factoring, multiplying things out, multiplying by conjugates. But here, these functions are all continuous. So all we're doing is using this property right here, which means our limit is essentially done. We just need to simplify this. This is the square root of 0 minus 4, so a -4. 0 minus 9 divided by -9. So this is the square root of 4/9. You can take the root of the numerator and denominator separately to get 2/3. So that's all the limits are. whenever you know you're dealing with a continuous function. Any questions at all, folks, on running through part A? Okay, it's a good idea to kind of pause here because section 2.5 is like a huge shift from how we've been doing limits prior in section 2.4. Let's keep this in the back of our mind and just compare for comparison's sake. Section 2.4, we had to use algebraic methods to evaluate our limits. And this is how it worked down here. We started with functions which were not continuous whatsoever. You can't put in a zero in this location because you've divided by zero twice. So we did some algebra. We added the fractions together, did some cancellations, but this cancellation was massive. Once we cancel the t and the t, and it's just 1 over t plus 1, that's now a continuous function. So we just directly substituted 0 in right here and finished off the limit. Only difference between this problem and this one was this one is continuous from the start. We didn't have to do a single thing algebraically to this. We just directly substitute. So that's the name of the game in section 2.5. We'll try it out a few more times, but really there's not too much left in these notes after these. Let's give this next one a try. We're taking the limit as we go to 0 of an exponential function with a square root function in its input with a degree 2 polynomial as the input to the square root function. That's just dealing with theorem 8 multiple times. We have 3 continuous functions. So 0 is in domain. We'll just plug it right in. So this becomes 2 to the power of the square root of something squared plus 1. We're heading towards 0, so by direct substitution, 0 goes there. Now we're just working out what this all equals. This is square root of 1 as a power on 2, which means it's just 2 power 1. Finally, the whole thing is 2, and we're done with that one. We're on our way. Kind of confusing in a way. Section 2.4 we did first. The limits were more technical because we have to do algebra. These limits are easier, but the reason 2.5 comes after is the whole concept of continuity is just tricky. So we left it for section 2.5 in the text. Any questions with either of these so far? Okay, I think this is the last one. It's expecting to do a lot more once we get to these limits, but this is pretty much the last thing to do. Notice if you directly substitute 4 in there, you get 19 in the denominator. That means this whole function, which is a rational function, has 4 in its domain. Rational functions are continuous on their domain, so we'll just use direct substitution again. So take that 4, plug it in for x. Really the only danger on this one is going too fast and just accidentally not squaring something right. For me, I feel like I'm usually a lot more reliable doing a function evaluation, or in section 3.1, function composition comes up, by putting in these little placeholder symbols. So we'll take advantage of that strategy quite a bit in this course. 4 goes here, here, and here, wherever the x's were. Now let's work this out. We have 16 minus 4 plus 10 up above. Below, we're looking at 20 minus 1. So let's see here. This is 26 minus 4, so a 22. Division by 19. And we're done at that spot. 19 is a nice prime number, so no way for this to reduce. Well, we did it, folks. These are the limits that can come up when we're dealing with continuity in section 2.2. Not a whole lot to say because continuity is a powerful technique. As soon as you have a continuous function, you're really just doing nothing different than a function evaluation. But any last questions at all, folks, before we close out this section? Okay, well, we worked really hard on limits. Spent a little bit more time on here than the day-by-day schedule indicated, but spending a little bit extra time in chapter 2 is usually well worth the effort. Because what we're doing here now next in chapter 3, starting in section 3.1, is turning this all around and showing how to define something called the derivative through a limit. We looked at this on day one of the class. We were saying, what do we even mean when we say derivative? Turns out it's all about slopes. But now we're in a really great position to say exactly what we mean when we say the derivative of a function at a value. To get there, we have to discuss this new concept called a tangent line. We drew this once, but now we're going to draw it again. So let's put down an XY axis where I'm going to mainly emphasize quadrant 1, just to make it visually readable. We have a function f we want to plot. So here's the function f. Put little arrowheads on those directions to say it just keeps on going in those directions. Here's y equals f of x. Now it says the tangent line to the curve y equals f of x, the one we just drew, at a point a f of a. So we need a relevant point on this. Let's make this a. The f of a is when we go up, hit the graph here, and get an output value, f of a. So the tangent line to the curve, y equals f of x, at the point here, a f of a, is a line through that point, the slope given through that limit. Kind of a weird limit. Part of our goal in section 3.1 to start out is to understand what that limit is even trying to say at this first place. But it is a bona fide slope, so we called it m. First, let's actually sketch this tangent line. It's going to be in blue. It's a tricky sketch because it has to hit this point. And there's lots of ways for my tangent line to hit that point. Like this line did an okay job, but let me kind of maneuver it just a little bit. This is sort of cheating. A little bit better. Not perfect. Doesn't have to be perfect. Let me not fuss with it too much, but last try. That's a little bit better. I like this line. This looks like a tangent line. If I drew it this way, that line's no good. Sure, it intersects through the point, but the problem with this line is if you're off the point and over here, this curve and that curve have nothing to do with each other. They're far too different. But this location is special because if you zoom in right here, a good tangent line has the feature that the curve in black should be pretty close to the curve in blue when you're nearby this point. So this one looks a little bit more like a true tangent line. We're going to compute a tangent line ourselves algebraically. We'll pull up Desmos, applying the curve in black, the tangent line, and we'll show as you zoom in on this, the tangent line is the best local linear approximation of the curve in black. So if we can get that line, we're doing calculus. It has equation y equals m. We need a special color for m. Let's go with this. X plus b. So now understanding what this limit is trying to say, it's all about computing the slope m of this tangent line. But has anyone noticed the problem with even computing that slope m? What would be the trouble here algebraically? Let's maybe start by just writing down the formula. We want a slope m. The slope m is through formula y2 minus y1 divided by x2 minus x1. And now that the formula is revealed, anyone see what the issue is with computing that slope using this formula? Exactly. The response from class was, you can't even use this at all because there isn't 2 points on this graph whatsoever. There's just the 1 point. So this is where calculus comes in. Notice there's a limit right there. This limit is going to allow us to still use that formula with just this 1 point. That's really kind of weird. It's a little trick. But we're really using 2 points. Here's the next thing that comes into play. It just so happens we need a second line. So I can't do the exact slope at A. So the thought is, make a slightly different value by going like this. A plus H. So this is just slightly to the right of A. If I go A plus H, there'll be a new value way up here. and go directly to the left, that height is f at a plus h. So think of h as a very small quantity. It can either be positive or negative. I plotted it as a positive value. That's why it's to the right of the point A. But I can only do one picture really, so I just chose put it towards the right. Now there's 2 points on here. But the trouble is we're not looking at the tangent line any longer, right? This is a whole different line. It's going to connect through here. I still don't want to fill that in too much. It's going to connect through here and here. So it goes off like this. Down like that. We call this one a secant line. But at least with the secant line, we've got 2 points now. So let's start indicating how everything is going to go back into the slope formula over here, putting it all together at this stage. We have to have an x2 and an x1. I'll think of a plus h as x2, a as the x1. y2 and y1, these are just function values. So I'll think of this f at a plus h as y2, the f of a as y1. Plugging this all in, we can now say m, that's the slope we really, really want, but it's only approximately equal to the slope of the secant line. Let's write it down regardless. The slope of the secant line would go f at a plus h minus f of a, so that's just y2 minus y1. In the denominator, you'll go x2 minus x1, so that's a plus h minus a. And our slope again is only approximately equal to that. Another thing that happens though, even though it's approximately equal, there's a nice simplification. This slope is approximately f at a plus h minus f of a. Cancellation in the denominator gives us just h. So that's why there's just an h right here. Last thing we need to tie in is, what is this limit actually doing for us? But any questions at this point of building out this graph? Okay, well, notice what the limit does. It's making h small. It's getting closer and closer to 0 in the limiting process. What happens when h gets small is at this point, moves closer and closer to a. We're not concerned with h is exactly 0. In fact, the value of the limit is irrelevant when you plug in 0 into this whatsoever. We're just wondering, what is the slope getting closer and closer to as h down here gets smaller and smaller? Graphically, it's going to do this. Let me zoom in a bit. If a plus h gets closer to the point A, because h is going to 0, that means the secant line, oh, I drew it as 2 parts, but the secant line is going to start changing like this. It's going to get closer and closer to the actual tangent line until it looks like it's just totally overlapping. If we can evaluate that limit, we get m. So it's a very dynamic picture where the secant line keeps on changing. The slope here keeps updating, becoming ever closer to the slope we really want, that slope m for the tangent line in blue. So finally, we get to say, putting this all together, m is now directly equal to a limit as h goes to 0, f at a plus h minus f of a divided by h, and we'll call this right here the slope of the tangent line. We'll also call it in these notes, and we'll emphasize that even more in section 3.2 and the rest of chapter 3. This is equal to the derivative of f at x equals a. So that's what we're going towards. In fact, because the derivative is so important, and it's through a big limit like this, we'll use a common notation like this. The slope of the tangent line m is equal to f at a. This is incorrect. That's just a function value. The way you emphasize it's truly a derivative, there'll be multiple ways, but the fastest way is Newton's prime notation. That symbol right there. That's not an exponent, it's not power one. It's a prime symbol going this way. So try to angle it as much as possible to not get mixed up with other potential symbols. So this symbol right here is the derivative of f, and all it's trying to get for us is a slope. So this is the picture that we investigated on the first day of class, but now we have all of the actual details. That right there is the only reason we did chapter 2. We want to know more about derivatives so that we can get to integration, but the only way to do that is through a limit, unfortunately. But it does mean we get to practice all the things that we did in chapter 2. So that's what's going to go on in the next examples down below. But any questions or comments so far, folks, on the discussion here? Okay, and maybe one other takeaway. All of this is in the book for sure. But you know, when you look at a math book and you see a diagram like this, it doesn't necessarily serve you a whole lot. It's too visually overwhelming. Even this diagram we're looking at right here, it's losing its value because it got filled in so much. What's most important is building it out step by step. So anytime you see something technical with diagrams in your textbook, if you can build out the process step by step, like we did here, that's really the way to retain that kind of information. Some people can look at these diagrams and just see it all at once. I think for most people, it's just too much. You need to focus on the components, the individual trees, not the whole forest, in other words. So getting in a habit of doing these kinds of things is not just great for math classes, any technical amount of information. It's about how it gets built. It's not about the final picture. But let's put this all to good use. For this example 1 right here, our goal is to actually find the equation of the tangent line to this function, and it's going to be at a point 1, 2. Definition 2 is just reduplicate it down here. Here's our equation for that tangent line. And it is kind of an adventure to get through this one, so we'll take our time on it. Now, I have to be honest, I'd rather do this one with x power 2, but in WebAssign, I didn't find any good ones with x squared on there, so I assigned one with x cubed. That means we have to do one like that as well to support the homework. But the reason I'm mentioning all that is, if this was an exam question, I would probably drop it down to x power 2 just to save on some steps. Think of this problem as now kind of a good algebra review. First thing we have to do is, well, notice the conflict already. This is y equals f of x. They didn't say there's a f of x there, but it's implied to be that, the x cubed minus 5x plus 6. Function notation is overwhelmingly used whenever we're writing down formulas in calculus, so we see the function notation here. So you could, if you'd like, to start off, just say f of x is x cubed minus 5x plus 6. So that's the function f in the definition up here. Next struggle about this is the number a. Notice it's everywhere. We do the tangent line at the point a, f of a. We take the limit of f of a plus h minus f of a. So we need to know, what is a in our problem? Has anyone spotted it? Here's a hint right here. You want to think of this point and then match it up to whatever point was provided in the problem. So pretty much this is the major tie-in right here. If you're thinking about this as the point coming from the definition above, whatever is the first coordinate, that's your a value. So in this problem, a is 1. Does that make sense, identifying the a? Awesome. With that out of the way, we're nearly there. We just have to run through the limit. So next step I would take is, we're coming up with a slope m. Violet here just because it's something to pay extra attention to. It's our new major thing we're looking at. Here, all I'm doing is just filling out the definition, limit. H goes to 0, f at, not a plus h. Let's plug in 1 right here. 1 plus h minus f of 1, all divided by h. The moment we found the value of a, that's a good idea to plug it in right here. And this is the point at which we want to be really careful. F at 1 plus h is not a fast computation. its function value, its function composition as well. So let's take our time with that part right there. So it's relative to this function f we're working on. F at 1 plus h becomes, in place of x cubed, put it in parentheses like we were doing in just the last section of continuity, that go minus 5 times, another parenthesis, plus 6. No matter what goes in here, if it's just an x, you have the x cubed minus 5x plus 6. If it were a y, we would go y cubed minus 5y plus 6. And if it's a 1 plus h, we go 1 plus h cubed minus 5 times 1 plus h plus 6. So we could drop that right here in the limit. But sometimes when these get kind of overwhelming algebraically, it's a good idea to just work them out in the margin. Whatever this comes out as, we'll just drop it back inside here. So for the moment, all we're doing is expanding all this stuff. First, I'd probably think of this as a 1 plus h, multiplying a 1 plus h times a 1 plus h. I'm just going to FOIL this out by first principles. Minus 5 times 1 plus h plus 6. I put brackets here just to indicate I want to FOIL out those two first, just a personal choice. We'll get 1 plus h. FOILing that all out, combining the terms in the middle would just give us a 1 plus 2h plus h squared. Might as well distribute here. We have minus 5 minus 5h plus 6. A little bit more algebra, we just need to FOIL one more time. Not exactly FOIL, but the same kind of process. But any questions so far? Okay, first, I just visualize the 1 is distributed into the group to the right with the bracket. Times 1 just gives us 1 plus 2h plus h squared. Then move over and distribute h into that bracket. We'll get plus h plus 2h squared plus h cubed. Now from here on out, I'm just copying what we have, minus 5h, excuse me, minus 5, then minus 5h, plus 6. Now finally, we have like terms we need to combine. So let's see, as far as the constant goes, this is a little bit tricky. Let me use this to just help me visualize it. Those are the constants, so that means we have a 2. Let me try again with that. There we go, that makes it look more official. The next kind of term is in degree 1 for the variable h. So there's a 2h, there's a h here, and then a negative 5h. So 3h minus 5h gives us negative 2h. Then from beyond that, it gets a little bit easier because there's just an h squared, 2h squared. So it's a plus 3h squared from that. And we're working our degrees up on this. The last one is just plus, or hang on, I made a mistake here. Let me try again. Back to the h squared, back to the drawing board on that. It's h squared plus 2h squared, giving us 3h squared. We can't change the degree when we're adding them together. We're just changing the coefficients. Does that make sense with that weird error I put down? Awesome, sorry about that one. Then after power 2, there's just h cubed left over. So go plus h cubed. And that's tedious. This happens once on WebAssign. I'm not in a habit of asking these questions that's that tedious algebraically, but my hands were kind of tied with the WebAssign, so we ought to do one as well. Major reason we did this one. Well, that part's done. In the spirit of just breaking this up, dividing and conquer, let's now do f of 1 as well. F of 1 is not so bad. We just go right back up here. It's 1 cubed minus 5 times 1 plus 6. So that's 1 minus 5 plus 6, which gives us a positive 2 altogether. So there's a next step here where we just plug everything back into the limit. So we're back to limit. H goes to 0. First, for the f of 1 plus h, I'm just using all this stuff right here, dropping it right in. So 2 minus 2h plus 3h squared plus h cubed. Now we're at this position, copying in the formula, minus f of 1 we've already computed, but if you really look closely at this, we didn't actually have to compute it. I often forget this myself because when you're looking at a point that's on the graph of your function, you can also say that this is just a new way to say f at 1 equals 2. So that was actually a foregone conclusion the moment the point was supplied. But it's good to double check. If the problem was flawed, we would have known right away by calculating f of 1 ourselves. I'm not in the habit of writing up flawed questions, but it's good to know that there's a way to check that kind of stuff. So I copied h down below. This is our limit to do, which means this is just a problem that we saw in a section 2.4. So that's where all that work on limits finally comes back together, working on this one. And notice the struggle here. In the original definition, continuity is immediately off the table because you can't put 0 in that denominator. In other words, this function that we're writing down here, expanded out here, is a rational function in the variable h, but it is not continuous at 0 whatsoever. In section 2.4, we have to do something algebraically to it. Oftentimes it was just simplify and factor. What simplifies? Well, positive 2 and negative 2 cancel. That means we now have the slope m is equal to limit h goes to 0 of, all these terms involve just h now. So we could factor it out, leaving h times negative 2 plus 3h plus h squared. So that's the factoring step we took oftentimes in section 2.4. It's down divided by h. And the whole reason we wanted to factor really is so that h cancels off. When that h cancels off, we are left with a continuous function. So now it is m equals the limit as h goes to 0 of just negative 2 plus 3h plus h squared. That's just a polynomial in the variable h. Every polynomial is continuous on its entire domain. And so now this problem turns into a section 2.5 question using continuity. But continuity, when we're doing it analytically like this, no graph in sight, just means direct substitution. At the next step, you will directly input 0 for h here and here. And my claim is that will give us the exact slope of the tangent line. So let's write out that last step. M is going to be equal to negative 2 plus 3 times 0 plus 0 squared. And then finally, we've got a slope m equals negative 2. We want the whole equation, but that's the whole battle right there. If you can find the slope of the equation, we have a slope and a point. Our work is just about done. Any questions at all, folks, getting down to that step there? Okay, so let's call this our next step of getting the tangent line equation. For me, I usually just copy the book's approach. I go y minus y1 is equal to a slope times x minus x1. That slope is special though. Let's tie that together with the one we were analyzing. As far as the y1 and x1 goes, it's just right back up here. So you could say that this is x1 comma y1 if you prefer. So 1 and 2 for x1, y1. Just drop in the values down here and we'll get our equation. So this goes y minus, there's still 3 substitutions to make, so you have to be very careful. y1 is the second coordinate 2. Equals the slope m. We computed that painstakingly and we got negative 2 as our result. So that's our second substitution in here for the slope. X is a variable, so we leave it in just as like the Y. Minus x1 is just the first coordinate, which we called A right up here. So it'd be x minus 1 in this location. Standard things we would do here is solve for the variable y. So let's maybe expand over here first. It's y minus 2 equals negative 2x plus 2. So y equals negative 2x plus 4. And that was our target. All of this cloud of math above here was just so we could get to here. I'll box this one out because, again, our work is all over the place. This is just my way of emphasizing that's what we wanted, whenever there's lots of work on paper. The hard thing about this is deciding what did we just compute. So we're going to take a look at this with a graphing calculator. But any questions at all, folks, on getting down to here? It is quite a process, so we'll practice this some more when we come back on Thursday's class. But for the last 5 minutes, let's just investigate what it is we even did. We want to plot this function to start. You can call it a y equals or use function notation if you prefer. F of x equals, either way gives you the same results. X cubed minus 5x plus 6. But we were very concerned when we were at the point 1, 2. So that's not quite there. Right about here. Hey, there's the point. If we put a tangent line slope on that, it should have a negative slope. The curve is going downwards, in other words. So getting the negative slope here is really encouraging. And the full check is to go y equals negative 2x plus 4, our whole tangent line. Now let's blow this up a little bit more. Here's the point 1, 2, where we're trying to find the tangent line relative to. And what makes it a tangent line is line in blue is the best local linear approximation of the function f of x. Here's what we mean by that. If you zoom in on this point, you'll notice that the difference between the function in red and the tangent line are extremely hard to spot. So if we're in the neighborhood of between 1.005, 1.01, which is in the middle of the 1, notice that there is essentially just no difference between these two. Let me try to find the point 1. Actually, must have zoomed away from that. Here it is. There we go. So right at 1, 2, no apparent difference between the function and the tangent line. The way this is relevant to us is sometimes equation solving is extremely hard, especially if differential equations come into the mix. But if you can exchange this really complicated graph for the tangent line, because all you care is about nearby 1, all of your algebra gets massively simplified. So this is the check that you have a real tangent line. But notice how sensitive this is as well. If you said the slope was negative 2.001, you're way off. That's nowhere near a tangent line. And that was a very, very small difference. So there is only one tangent line. It has to have slope exactly negative 2. Well, any last questions, folks, on getting through this one? Leave the graph maybe zoom to about this level. Okay, well, that's all I have for folks today. This is kind of an early look. We'll look at more tangent lines on example part B here. We'll start taking derivatives, which is just really focusing on the slope part of it. When we come back for next class, it'll be just kind of more of the same, practicing these sort of limits. But have a great afternoon, folks. If you do have questions, I'll be happy to help out. Otherwise, I'll see you all in Thursday's class. Yep, take care.